Imagine a place in the universe where gravity is so strong that nothing, not even light, can escape. We call it a black hole. The name sounds dramatic, mysterious, almost like science fiction, but it's not fantasy, it's real physics, and understanding it requires thinking a little differently about how space, time, and matter behave. To get there, let's start with something familiar. Picture a trampoline stretched tight. Now place a bowling ball on it. The fabric sags under the weight, creating a dip in the surface. If you roll a marble near the ball, it will spiral inward toward the center of the sag. This is a simple analogy for how gravity works. In Einstein's theory of general relativity, massive objects bend the fabric of space and time around them, and other objects move along those curves. Now imagine adding more and more weight to the trampoline. At some point, the sag becomes extreme, a deep well so steep that anything rolling nearby would fall in and never come back out. That's essentially what a black hole is. It's a region of space where the pull of gravity is so intense that nothing can escape, no matter how fast it moves. Not rockets, not light, nothing. The boundary around this region is called the event horizon. It's not a wall you can touch, but a point of no return. Cross it, and you cannot come back. Outside the event horizon, we can observe the effects of the black hole. Inside, it's hidden from our view, which is why black holes are both conceptually simple and profoundly mysterious. Think of it like a waterfall in a river. If you're far upstream, you can swim freely. Get too close to the edge, and the current drags you past the point where you can return. Once you've crossed that invisible boundary, the fall is inevitable. That's exactly what the event horizon does to objects approaching a black hole, except the river here is the fabric of space and time itself. Black holes don't just float around randomly. They are born from the collapse of extremely massive stars. Stars live in a delicate balance between the outward pressure from nuclear reactions in their cores and the inward pull of gravity. For most of a star's life, these forces are in equilibrium. But when a massive star exhausts its nuclear fuel, the outward pressure disappears and gravity takes over completely. The star collapses inward, shrinking smaller and smaller, until it forms a singularity, a point of almost infinite density. The singularity is cloaked by the event horizon, and together they form what we call a black hole. Now imagine you could watch a friend falling into one. To you, they would appear to slow down as they approach the event horizon, stretching out time until it looks like they almost freeze at the edge. From their own perspective, however, they cross the horizon without noticing anything unusual. Time behaves differently near black holes, bending and stretching in ways that defy everyday intuition. This bending of space and time, this extreme warping of reality, is what makes black holes both fascinating and difficult to truly imagine. Black holes don't just appear out of nowhere. They are born from the death of massive stars. To understand this, we first need to think about what a star really is. A star is an enormous ball of gas, mostly hydrogen, fusing atoms in its core. That fusion produces light and heat pushing outward, balancing the inward pull of gravity. For millions or even billions of years, this balance keeps the star stable, like a perfectly stretched trampoline. But this balance cannot last forever. Eventually, the star exhausts the fuel at its core. Without the outward push from fusion, gravity takes over completely. When a very massive star runs out of fuel, it collapses. The outer layers fall inward, and the core shrinks under the relentless force of gravity. For stars heavier than a certain limit, nothing can stop this collapse. The core compacts into an incredibly small point, what physicists call a singularity, where density becomes almost infinite. Surrounding the singularity is the event horizon, the point beyond which nothing can escape. The combination of singularity and event horizon is what we call a black hole. The singularity is where our current physics breaks down. It's a place where space and time curve infinitely, and our equations fail. Imagine this collapse like crushing a soda can. You press the can with more and more force. At some point, the walls crumple inward, creating a tiny, dense shape. Now replace that can with a star, and the crushing force with gravity. The result is a singularity, a point so dense that all the mass of a star is concentrated in an infinitely small space. The universe has no way of physically stopping this process, which is why black holes are inevitable in these extreme cases. Here's an interesting thought experiment. Suppose you could observe a friend falling into a black hole. To you, from a safe distance, They would seem to slow down as they approach the event horizon. Stretched out in time, their image reddened and dimmed. From their perspective, though, nothing special happens at the horizon. They cross it and continue falling toward the singularity, experiencing the intense gravity firsthand. This discrepancy is one of the most mind-bending aspects of black holes. The same event appears completely different depending on your frame of reference. It's as if reality itself has multiple layers, each obeying the same physical laws, but producing radically different experiences. Black holes are not just cosmic vacuum cleaners. They have structure, they interact with their surroundings, and they can grow. If gas, dust, or even stars venture too close, they spiral around the black hole, forming an accretion disk. As the material falls in, it heats up, releasing enormous amounts of energy and light. These phenomena are what make black holes observable, despite the fact that no light escapes from inside the event horizon itself. Observing these effects allows scientists to infer the presence and properties of black holes, even though we can never see the singularity directly. Some black holes are small, a few times the mass of the sun. Others, called supermassive black holes, lie at the centers of galaxies and contain millions or even billions of solar masses. These giants have likely been growing for billions of years, feeding on gas, stars, and even merging with other black holes. They shape entire galaxies through their gravity, influencing the motion of stars and the formation of cosmic structures. In this way, black holes are not just exotic curiosities, they are fundamental actors in the universe, quietly controlling the dance of galaxies across cosmic time. So what do we actually know about black holes? Despite their mysterious reputation, scientists have learned a great deal about these objects, not by visiting them, but by carefully observing their effects on the universe around them. Gravity, after all, doesn't hide. Even if a black hole swallows everything inside it, the mass it contains still tugs on nearby stars' gas and light. By tracking these movements, we can measure the mass size and sometimes even the spin of a black hole. For example, stars orbiting an invisible point in the center of our galaxy reveal the presence of a supermassive black hole called Sagittarius A. We cannot see it directly, but we can watch its influence like seeing a shadow on the ground and inferring the shape of the object casting it. Black holes can also grow over time. They are not static or passive. They actively interact with their surroundings. When gas and dust fall toward a black hole, they don't drop straight in. Instead, they spiral around it, forming a disk called an accretion disk. Friction and gravitational forces heat this material to extreme temperatures, emitting enormous amounts of light, X-rays, and sometimes even jets of matter traveling near the speed of light. These emissions allow astronomers to detect black holes across vast distances, even though no light escapes from within the event horizon itself. In 2015, a completely new way of observing black holes emerged: gravitational waves. These are ripples in the fabric of space-time produced when two black holes collide and merge. The first detection of gravitational waves confirmed that black holes not only exist, but also interact in violent and predictable ways. By analyzing these waves, scientists can measure the masses of the colliding black holes, the energy released in the collision, and even test Einstein's theory of general relativity under conditions far beyond what we can recreate on Earth. Perhaps the most striking achievement in observing black holes came in 2019, when humanity captured the first image of a black hole. Using the Event Horizon Telescope, a global network of radio observatories, scientists imaged the glowing ring of gas surrounding the event horizon of the supermassive black hole in the galaxy M87. The image was not a photo in the ordinary sense. It was a carefully reconstructed map of light distorted by extreme gravity. But it confirmed with stunning precision what theory had predicted: a dark shadow in the center, a glowing ring of accreting matter, and the signature of extreme space, time warping. This moment was like finally glimpsing the edge of a waterfall from the shore after decades of speculations. All of these observations show that black holes are not merely theoretical curiosities. They are real, measurable, and obey predictable laws. Their existence validates general relativity in the strongest possible way and provides natural laboratories for understanding physics under extreme conditions. At the same time, each new measurement raises deeper questions. How does matter behave when crushed into a singularity? What happens to information that falls inside? Could black holes eventually evaporate via Hawking radiation? Observations give us knowledge, but they also reveal the limits of what we can see and measure. In short, we know black holes exist. We know they warp space and time. We can measure their mass and spin. We can observe their accretion and even the ripples they create when they collide. Yet, despite all this knowledge, they remain one of the most profound mysteries in the universe, simultaneously revealing the precision of our theories and the gaps in our understanding. They are perfect examples of how science balances what we know with the questions we have yet to answer. Even though we can observe black holes in many ways, there is a vast territory of what we don't know. Black holes push the limits of physics to the extreme, to places where our current theories break down. At the very center of a black hole lies what physicists call a singularity. This is a point where matter is crushed to an infinitely small volume and density becomes infinite. Space and time, as we understand them, no longer exist in any meaningful way there. Our equations give nonsensical answers, and we have no way to directly describe what actually happens. It's as if the universe has a secret that we can only infer from its effects, not observe directly. One of the most perplexing mysteries is the information paradox. In quantum mechanics, information about a system, the precise arrangement of particles, cannot be destroyed. Yet, according to classical descriptions of black holes, anything that falls inside, including its information, seems to disappear forever. How can information vanish if the laws of physics insist it cannot? This contradiction between quantum mechanics and general relativity is unresolved. It's not a minor problem. It's a fundamental tension at the heart of physics. Black holes are forcing us to rethink our understanding of reality itself. Stephen Hawking offered another twist. He showed that black holes are not completely black. They can emit what is now called Hawking radiation. This radiation arises from quantum effects near the event horizon and suggests that black holes might slowly lose mass and even evaporate over unimaginably long timescales. If a black hole can vanish this way, what happens to the information it contained? Does it escape in some hidden form, or is it lost forever? Nobody has a completely satisfying answer yet, though numerous theories attempt to reconcile these issues. The challenge of understanding black holes also lies in the nature of observation. We cannot send probes inside an event horizon. We cannot directly experience the singularity. We can only measure the surrounding effects, the orbiting stars, the heated gas and accretion disks, the gravitational waves from mergers. These observations provide extraordinary insight, but the true interior of a black hole remains completely inaccessible. In a sense, black holes are perfect mirrors for our own scientific limitations. They show us exactly how far our models can take us and where our understanding collapses. Black holes also challenge our intuitions about space and time. Near the event horizon, time slows dramatically relative to a distant observer. Light is stretched into longer wavelengths. Concepts that seem absolute in everyday life become fluid, malleable, and relative. Gravity and quantum mechanics are no longer separate. They are intertwined in ways we are just beginning to grasp. Black holes are laboratories for a theory of everything, a framework that could unify the laws of the very large with the laws of the very small. In this way, black holes are both terrifying and beautiful. They are cosmic objects that test our understanding of reality, pushing it to the extreme. Every paradox, every puzzle, every gap in knowledge is an invitation to think more deeply, to question the assumptions we take for granted. They remind us that the universe is far stranger than intuition allows, that there are limits to what we can observe, and that some of the most profound truths lie hidden just beyond the edge of our understanding. Humans struggle to explain black holes because they push the very limits of our perception and understanding. Our brains evolved to navigate a world of apples, rivers, and trees, not singularities and warped space-time. We are built to understand gravity as a gentle pull, not as a force that can stretch time itself or crush an entire star into an infinitesimal point. The concepts inside a black hole are so extreme that our intuition almost completely fails. Even the language we use, words like nothing escapes or infinite density, strains our minds because we have no real life reference for infinity or a region of space where time slows to a crawl. Part of the difficulty is observational. We cannot enter a black hole, and we cannot see inside the event horizon. We can measure their mass, watch their effects on surrounding stars, detect the light from infalling gas, and even record the ripples of gravitational waves when black holes collide. But every one of these observations is indirect. We are trying to understand the inaccessible by studying its shadows and echoes. It is like trying to understand the shape of a waterfall by watching ripples at the edge. We get glimpses, but the interior remains fundamentally hidden. Another challenge is theoretical. Black holes exist at the intersection of general relativity and quantum mechanics. General relativity, Einstein's theory, describes gravity and the warping of space, time on large scales. Quantum mechanics describes the probabilistic behavior of particles on extremely small scales. Both theories work extraordinarily well in their own domains, yet they give contradictory answers when applied to black holes. Time, space, matter, and information behave differently in each framework, and reconciling these differences is one of the greatest unsolved problems in physics. Black holes highlight a profound tension. In our understanding, the universe seems simple in principle, yet reality resists our attempts to fully describe it. The way we think about causality and observation also complicates understanding in everyday life, because in effect are straightforward. Drop a ball, it falls. Turn on a faucet, water flows. But near a black hole, time itself behaves differently depending on your point of view. A falling observer experiences events in a linear sequence, while a distant observer sees those same events stretched or slowed. The universe no longer follows the rules we are comfortable with. Our mental models, based on normal conditions, simply cannot handle such extremes without careful mathematical tools. Even the most brilliant physicists approach black holes with humility. Feynman himself would emphasize that it is not a failure to be confused, it is an opportunity to understand the limits of our knowledge. Black holes expose the boundaries of human reasoning and the gaps between intuition and reality. They force us to think creatively, to rely on precise observation, to construct models that predict phenomena we cannot directly experience. In this sense, the struggle to explain black holes is not a flaw, it is the essence of science. Finally, black holes challenge our philosophical assumptions about reality. They ask questions we cannot answer definitively. What happens to information inside a black hole? Can we reconcile infinite density with the laws of physics? Are space and time fundamental or emergent? Humans struggle because these are not just technical questions, they are questions about the nature of existence itself. Black holes remind us that the universe is more complex and subtle than our ordinary experience suggests, and that intellectual humility is as important as curiosity in the pursuit of understanding.